Hey Math Rockstars, this video takes a look at piecewise functions. So I am on the same set of guided notes that we use for the rule of 4, and you may want to look those over a little bit and then flip over to the back and we'll take a look at piecewise functions. We're going to look at specifically what a piecewise function is and then apply the rule of 4 to a specific piecewise function example. So a piecewise function is a function that's made up of different components. It might look like a parabola on one side, so maybe it starts off looking like this. And then all of a sudden, it takes a turn and becomes linear in one direction, and then maybe it takes another turn and becomes linear in another direction. So it is really quite difficult to describe a piecewise function using just one equation. It's got one graph, there it is, but this first piece would have something with a square in it to describe this, and then the next two parts are definitely some kind of line. There's one line with a positive slope and then a third line with a negative slope. So this particular piecewise function has three different parts to it, and I would really need three different functions to describe them. So there's a notation that's used that looks a little weird. For example, here's a piecewise function f of x, and it's going to be defined this way. So I am not going to write just one equation for a piecewise function. I'm going to need a couple. So here's a piecewise function that has two components. The first component is going to be x minus 2. And that's going to be the case. I'm going to use x minus 2 if my x values are less than 3. And if my x values are 3 or greater, I'm going to just say, well, my function is going to take on the value of 3. So x is greater than or equal to 3. And you're probably saying, what the heck does that even look like? Well, let's draw out a little sketch and see. So here's graph. So my independent values along the horizontal and my dependent values along the vertical axes. So when my function is less than 3, so 1, 2, 3. When it's less than 3, I'm going to use x minus 2 as my function. You could think of this as y equals x minus 2. So from 3 on to the left, my function is going to look like a line that goes through negative 2 on the y-axis and has a slope of positive 1. All right, let's put there's negative 2 and negative 1, 2, 3, 1, 2, 3. It's negative 3. There's negative 3. So it's going to go through negative 2 and then has a positive slope. Up 1, over 1, up 1, over 1, up 1, over 1. So starting at 3 and going backwards, my function looks like that line. I am not going to continue it in this direction because after 3, in fact starting at 3, I need a whole other function. I need something else. This piecewise function is being described in some other way. Something else, when it gets to 3, my function changes. So I can't include 3 in the x minus 2 part of my equation. So I'm going to draw an open circle there at 3. Let's look at the second part. So the second part of my piecewise function says, okay, at 3, the function is going to take on the value 3 forever. So you could think of it as y is going to be equal to 3, or f of x is equal to 3, from 3 on. So at 3, my function takes on the value of 3 and it stays there forever. Before x equals 3, That line doesn't exist. So there's a graph of a piecewise function. Let's look at one more. I'm going to put this on a separate sheet. And if you want to include it in your notes, you could, or you may want to watch and then grab a second sheet of paper, note paper, and rewind, or try this on your own. So here's another piecewise function, g of t. Maybe the independent value is time. And I'm going to define the piecewise function g of t in this way. When t is less than or equal to 0, my function is going to use t squared to describe it. And when t is greater than 0, my function is going to use the square root of t to describe it. So once again, I'm going to have two parts to my piecewise function. All right, well, let's see. What's this going to look like? So let's do the first piece. When t is less than or equal to 0. So here's t along my independent, f of t along my dependent, and here's t equals 0. When t equals 0, it's going to be a parabola, right? Y equals x squared, that's just a parabola. So I know it's going to look something like this. But on the right-hand side, where t is greater than 0, I need to use something else. So I don't want this leg here. I just want it to go as far as 0. But this part exists in my understanding, or might help me graph it, but it doesn't actually exist as part of the graph of this piecewise function, because after 0, oops, I need to cross that out, I'm going to use the square root of t as my graph. So the square root of t, the square root function, you may not have seen before. Y equals the square root of x. That looks like a sideways parabola. And we'll be talking about this in the module on radical functions. But for today, you could just sketch it in. It'll look something like this. Definitely a weird looking function. There's an open circle here, but it's getting filled in by the other function, so there's not going to be a gap in the same way as my other example. If you're wondering where that graph comes from, so if this is t and this is the square root of t, let's just take a couple of numbers. We'll look at this from the rule of 4, the data piece. If t is 0, the square root of t has to be 0. If t is 1, the square root of 1 is 1, so 0, and then if this is 1, there's 1. The square root of 2 is kind of difficult to graph, so let's think about the next perfect square, the square root of 4. 2, 3, 4. That would be 2. So 1, 2, and so on. You can kind of see how it's going to curve up quickly at first and then start to level off. So there's another example of a piecewise function. Going back to our notes, and let's use the rule of 4 and look at a specific piecewise function example. So here's the context, the verbal part. Mara earns $9 an hour for the first 40 hours that she works in a week. $9 an hour for the first 40 hours. She earns $12 an hour for each hour over 40 that she works in a week. So she's going to earn $2 more for each hour over 40 that she works in a week. So these look like two different linear functions. My first linear function is going to be going up by 9 every time. My second linear function is going up by 12 every time. So this is definitely a piecewise function. My rate changes, goes from 9 to 12. let's think about what my domain or my independent values might be in this case. Well, maybe Mara doesn't work at all, in which case she would be working 0 hours. So that would be the smallest. She's not going to work negative hours. She's going to just work not at all, or she's going to work some. So definitely starting at 0, but then what about the other end of the domain? Let's see, well, there's 7 days a week, and if she worked 24 hours a day, well, that would give us 168, but that's a lot of hours and is definitely unreasonable. So it doesn't really make sense to put 168 hours there. She would be a very sick individual if she worked that often. I don't know. I wouldn't even want to think about that. So let's think about something a little bit more reasonable. Let's say that she ends up working over the course of the week for 60 hours, so 20 hours of overtime. So she could work up to 60 hours. So there's a possible domain from 0 to 60. And then a range, my dependent, that's going to be the amount of money that she earns. So if she doesn't work at all, then she's definitely not going to earn any money. And to figure out the upper ends, or the maximum part of the range, well, let's see. When she's working for the first 40 hours, she's earning $9 an hour. So that'd be 9 times 40. That's for that first 40 hours, so that'd be $360. And then she switches to her higher pay of $12 an hour. So if she works for 20 hours more, she's going to be earning $12 an hour. So 12 times 20 would be $240. And 360 plus 240 would be $600 altogether. So the range is $0 all the way up to $600. So there's a really short way to describe this piecewise function in terms of its context and its domain and range. What about in terms of an equation? Well, it definitely looks very linear. Let's set some variable choices here. The domain, our independent variable, what's changing is time. So maybe we'll say that's t for time. So t could be the number of hours worked. And then the range, the dependent values, all have to do with money. How much money is she earning? So d of t would be the amount of money. Amount of money earned. Now let's write an equation. The first part, so let's see, d of t. So the first part will be for those first 40 hours. So if t is less than or equal to 40. Well, for every hour she works, she earns $9. 9 times t, 9t. After that, so when t is greater than 40, so at 40, she's still earning $9 an hour, but anything more than 40, so that's why it's going to be greater than here, not greater than or equal to, but greater than 40, then she's going to be earning $12 an hour, so 12 times the number of hours worked. So there's my model, my equation for the piecewise function. What about a table of values? What does that really look like? Well, let's see. Time and dollars depending on time. If she works no hours, she earns no money. If she earns works 1 hour, she earns $9. 2 hours, $18. And that kind of goes on, right? All the way up until she hits 40 hours, then she's earning $360. Now the rate changes, so at 41 hours, she now has $12 more than 360. She's going to earn $372. At 42, $12 more, $384. And that will continue all the way up until you get to 60. So there's a table of values that you could use to describe this particular piecewise function. And then the last will be a graph. So let's make a graph. And I'm just going to have the first quadrant because I'm not going to have negative time. My independent horizontal axis is a time axis. And my dependent vertical axis is dollars of time, D depending on T. And my domain goes from 0 to 60, so maybe I'll go up by 20s here, 20, 40, and 60. And my range goes up to $600, so here will be $600, and maybe I'll sort of note halfway, 300. So dollars is in, my D of T is in dollars, and my T is in hours. I'm just including the units on my graph. First part is definitely a linear function. At 0 time, there are $0. At 40 hours, there are $360 earned. So it's going to be a linear function looking something like this with a closed dot at the end. I'm including 40 hours, so I'm including that 360 in my graph. And then it's going to jump because once she gets to a full 41 hours, her money increases. So at 40, I'm going to jump up here. And from here, it is going all the way up to 600 at 60 hours. So the slope's going to be a little bit steeper here. Now, if I had connected that all the way back down to my origin, you would see that that line is a little bit steeper. This is the $9 an hour, 9t, and this is the $12 an hour, 12t. So the 12t function is a little bit steeper, but I don't need to include that red part that I kind of sketched in. I just need the blue part. So there's the graph part of the rule of 4 for our piecewise function.